Hi guys, today I'm going to show you the full solution of the exam paper in 2022, Time Zone 2, Higher Level, Paper 2. Alright, no bullshit, let's go. Question 1, and you may pause the video here and read the question first. After finish reading, continue the video. Okay, it's good practice to always put down symbol to all numbers you see. For instance, you can see radius is 1.8, so we put down R, stand for radius. 20 meters per second is the speed, so we put down V here. 1.2 kilogram meter negative 3 is the density, so we put down rho here. And next one is question A. Outline why a force is acting on the airboat due to the fan blade. So it's about forces acting on the air and on the boat. Let's complete the force diagram above. As the blade is rotating, there is a force acting on the air particles. So force on air. And by Newton's third law of motion, there should be an equal but opposite force acting on the blade, and as the blade is attached to the boat, so which is essentially the same as acting on the boat. So that's how we complete part A. Part A, firstly, there is a force acting on air by blade. By Newton's third law, there should be a force acting on blade by air. Alright, part B now. Here we have a boat tied to the riverbank using a rope, and the rope is normal to the bank. And a van propels the air, making boats moving at a maximum speed. Maximum speed is a key word here because it implies that it's a constant speed. There's no acceleration. Okay, next one. We're going to show that the mass being propelled should be 240 kilograms in every 1 second. And to do so, let's take a look at the blade rotation and the air that it creates. As the blade is rotating, it's drawing a lot of air going through it. And this air will go through the blade like going through a tunnel. So what is the mass of air going in this tunnel? The mass going through should be something to do with the density, mass over volume. The mass would therefore be density times volume. The volume of a cylinder is cross-sectional area times height. So the density, which is 1.2, the cross-sectional area, which is pi r squared, and lastly times the height, which is how far can it travel in 1 second. According to the page on the left, it's 20. So putting everything into your calculator, you should see 244. And note that another exam technique here is when the question asks you to put down show that about, make sure your answer is at least one more significant figure more than the question suggests the target. So you should always leave your answer here 3 sig fig or more. As the given one is 2 sig fig, then you should give at least 3 sig fig. Alright, let's move on to part B2. Here we have the tension in the rope should be about 5,000 Newton. And let's take a look at the forces acting on the boat. The forces acting on the boat, which is firstly a forward force of the force given by the blade. Next one, we have a backward force. It is the tension by the rope. And these two forces, they are balanced so that the boat is still stationary. Okay, and these two forces, how do we link them together to show that its value is roughly 5,000 Newton? Firstly, F and T, they are the same. And the force acting onto the blade is the rate of change of momentum of it. So it is the mass over T times the speed. In every 1 second, there are 240 kilograms of air passing through, and it's passing through at a speed of 20 meters per second. So the answer is 4,800 Newton, and once again is one more zig zag greater than the show that target value. Alright, next one, part C. Here we have a new graph, and this is a speed against time graph. And you can see that in the beginning, the boat was stationary. Once the rope is untied, then the boat would keep on speeding up and speeding up. However, it's not speeding up forever. It will speed up significantly in the first 20 seconds, and after the first 20 seconds, you can see that it's still speeding up, but slowly. Its acceleration is slower than before. And let's take a look at the question on next page. Let's take a look at part 1. Why the boat would reach a maximum speed after a certain time? It's because as the boat is moving, there is a constant driving force by the blade. But there is a backward force. It is a resistive force. This resistive force could be a result of the air drag, and also it could be a result of the water drag because it's moving on the water as well. So the forward force is a constant force, but the backward force, the resistive force, is a variable. It's increasing with the speed. The faster the boats move, the greater the air resistance. Just like when you're riding a bicycle, if you go faster, you'll experience a stronger wind hitting your face, hitting your chest. So at the moment of the resistive force as the same as the forward force, these two forces will be balanced and there is no resultant force. So the short answer here is the resistive force increases with the speed. And there is one point, the resistive force is equal to the force by the blade. That's why there's no resultant force and no acceleration. Estimate the distance of the airboat travels to reach its maximum speed. Let's head back to the graph. In the speed time graph, we study the area in the graph to get its distance traveled. And now you should estimate the area in the graph. How do we make estimation here? We make estimation by creating different objects, different sections. From 0 up to 15 seconds, let's make it a triangle. From 15 up to, for instance, 25 seconds, let's make it a trapezium. From 25 up to 40 seconds, let's make a third trapezium. And that's how we make a good estimation on the overall area in the graph. Of course, it won't be a perfect estimation, but it's fair enough. And how do we get this area? We have half base height for the triangle. For trapezium, we have its area being the upper base plus the lower base times its height divided by 2. So the distance moved by the boat is actually the area on the graph. And it is the triangle the trapezium, and the trapezium. And putting all the numbers in your calculator, you should get a number very close to 510 meters. And don't panic if you don't get this number. As long as you create your own diagram correctly, as long as you make all the area add up together, and your final value lies within the range in 480 up to 460 meters, then you're good to go. Part 3. Let's deduce the mass of the airboat. Deducing the mass of an airboat probably is about the net force equals to ma. The mass is the unknown, which means we should be able to get all other informations. For instance, the net force. What was the net force acting on the airboat? Note that in part B, we had the boat attached to a rope, and there was a tension, and there was a forward force, right? And previously, the forward force and the tension, they were given at 5 kilonewton. Let's reuse this number because now the boat is untied, which means the tension is gone and it leaves the forward force be the net force, 5,000 Newton. And acceleration is, with the help of the graph, we can get its acceleration. In a speed time graph, we study the gradient to get its acceleration. And don't get the very beginning point and the ending point, because to do so, you won't get the initial gradient. You will get the overall average acceleration. This is something we don't want. We want the initial acceleration only. And initially, the acceleration could be something like this tiny triangle. Rise over run, which means 4 and 4, making its acceleration be 1 meter second negative 2. Okay, that's how we get the gradient, initial gradient. It makes the mass of the boat be 5,000 kilogram. That's it for question 1. Here we have question 2. Please pause the video and complete the reading first, and then you may go on. Okay, after reading the question, it's a good practice to annotate all the numbers. First one is volume, capital V. Next one is temperature T, but immediately turn this number into Kelvin, which means by adding 273, and it will be Kelvin. Next one, pressure, pre. Okay, number of gas particle, which means it's capital N, not small n. Small n, however, it is the number of mole. By looking up your data booklet, what you see is PV equals small n RT. So we need one more substitution. And that substitution is capital N over N8, Avogadro's constant. What's left is substitution and calculator's work. And you will get your final answer be 2.3 times 10 to the power of 23 with no units. That's it for part A. Here we have part B1. And energy is provided to the gas, therefore the volume of the gas is expanded, but the temperature is held constant. So the B4 could be like in a small container. But after is that now the gas container is getting larger in size. So if there were 5 particles there, now these 5 particles, they are occupying greater spaces. But the number of particles remains unchanged, which means the volume increase. but the number of gas particle remains. By having these two together, you can deduce the density should be dropped. Part B2. How about the internal energy of the gas? Internal energy of everything is a very common definition in exam, which is the sum of total kinetic energy and potential energy of all the particles. However, note that it is an ideal gas. For ideal gases, there is no potential energy, which means right now the internal energy of the gas is actually the sum of kinetic energy of the ideal gas particle. And the number of gas particles remains unchanged. How about the average kinetic energy of the gas particle? So you have the number of particles times the average kinetic energy of the gas particle. For ideal gases, in topic 3.2, you can get the equation, which is 3/2 kT. Note that the temperature held constant, which means N unchanged, K unchanged, T unchanged. Everything is unchanged. Then we can conclude the internal energy of a gas is constant. Next one, question 3. Here we have only one sound wave source, but there is a metal plate in opposites. So even though there is only one source, we can still create a interference, a superposition. The first wave is the incident wave. Let's label this one as incident wave. And after hitting the metal plate, it will bounce back. And we can label this one as the reflected wave. The incident wave and the reflected wave, they will superpose. And these superposition, they are guaranteed to be the same amplitude, opposite direction, same wavelength, same frequency. And all these are the conditions of creating a standing wave, also known as stationary wave. The solution to A1 is the description of how is a standing wave being formed here, and how does the standing wave give you a variation in intensity. Let's begin with the incident wave superpose with the reflected wave. And therefore, a stationary wave is formed, creating nodes and antinodes. This is the very common description of formation of standing wave. Next one is at those points of the nodes. It means it is a destructive interference. It will give you a very low intensity. However, at antinodes, it is constructive interference. It's giving a very high intensity of wave. That's it for A1. In part 2, you are going to calculate the frequency of the wave. First, let's create the standing wave, like this one. The position of node are here. There is always no vibration, no amplitude at all. And the antinode, the air here, with the greatest vibration and loudest sound you can create. And it is suggested that the adjacent minima, which means node, they are separated in a certain distance, 0.12 meter. So like here, it's 0.12 meter. This is exactly half of a wavelength. So you can write down half of a wavelength is 0.12 meter, giving you one full wavelength is 0.24 meter. Next is V equals to F lambda. That's how you can solve the speed being 340 according to question above here. And then the frequency is unknown, but the wavelength is 0.24. By rearranging, you should get the frequency as 1400 Hz. In part B, now we're replacing the metal plate using a wooden plate. And by doing so, the reflected intensity is lower. Which means if there was a wave created like this one moving towards the metal plate, maybe the reflected one is almost the same size. But now using the wooden plate, the emitted wave is in this size, but the reflected one will be softer. However, something is unchanged. Their wavelength and frequency are unchanged. So what's being the same between the metal plate and the wooden plate is their wavelength and frequency, and even their speed. What's being changed is the amplitude, because the wooden plate will reflect the wave with lower amplitude. And amplitude is related to the intensity using this equation. Intensity is the amplitude square, proportional to its square. This is the first mark already. Intensity and amplitude are related. Because the reflected wave is now softer than at the antinode, which means at the constructive interference, it will be softer. But the node position and the destructive interference position, it will be louder. And because of the wavelength and frequency, they are unchanged, then we can conclude the position of nodes and antinodes, they are unchanged. Question 4, the question of electric circuits. Identify the laws of conservation that are presented by the Kirchhoff circuits law. They are the conservation of electric charge, which is, in formula sheets, summation of I equals to 0 in any junction. Next one is the conservation of energy. It is summing all the voltage will be 0 in any closed loop. And what's being required is these parts only. The rest are not required in the mark scheme. Part B, we have a circuit going along with an ideal voltmeter, which means its resistance is infinitely high. And then let's apply the Kirchhoff's law of conservation of energy in the loop over here. For the power supply, its voltage is EMF. Next to it, we have an internal resistance, which is voltage of small r, also known as the loss volts. Next, we have the voltmeter, voltage of capital R here, which is also the reading of voltmeter. Note that at this instant, the switch S is open, which makes the bottom line useless. We can just cover it. Okay, by studying the conservation of energy, we know that the energy gained is equal to the energy lost. So the EMF is actually the loss volt and the reading of the voltmeter altogether. But the loss volt here is 0 because there is almost no current passing through it. So you can put down I times small r equals to the reading, and the I times small r is 0 times small r, like this one. And therefore, the EMF is actually the reading of the voltmeter itself. Note that the question gives you two readings. One of it is when the switch is open, the other one is when the switch is closed. We are working on the switch being opened. so it's 12 volts. Part 2 is different now because we have some information about the switch being closed. Let's make it close here. And when it is closed, now the voltmeter read 8.0 volts. 8.0 volt is also in parallel with the external resistor, so it is 8.0 volt as well. Let's take the Ohm's law here. R is defined as the potential difference over currents. The resistance is 4. The voltage is 8 and the current is unknown, so we can get the current should be 2 ampere. And this 2 ampere current is running through the cell as well. So at the cell, we can take a look at the loss volts. Let's put down subscript small r to identify it is the calculation on the internal resistor. Resistance of internal resistor is unknown for sure, but the voltage, we know that it should be 12 minus 8 because the loss volt will be 4 inside the internal resistor. And then the current will be 2 amps. It makes it 2 ohm. Now it comes to part C. It's very complicated because there are 2 cells. The cell A is pushing in anti-clockwise direction. It's stronger. Then the cell B is pushing in clockwise direction. It is weaker. It makes the total voltage should be 10 minus 4. And the total resistance is the 1 ohm internal resistor and the 2 ohm internal resistor, they combine. So what is the total current? It's a simple math. It will give you 2.0 ampere. And this 2.0 ampere is running through the cell A over here. Let's take a look at the cell A calculation. There is a terminal potential difference across the very left and right of the cell A, and it should be equal to the EMF minus the loss volts. The terminal PD would be the same as the reading, which is the EMF minus the loss volts, the current times the internal resistance. So the answer for this one is 8 volts. And part 2 is removed from the exam because of some misreferencing. Now we move on to part D. Firstly, why electricity is a secondary energy source? Simply because it is produced from those primary energy sources. Okay, next one, part 2. What's mean renewable? Renewable, which means the rate of production is greater than the rate of consumption. By the way, it's a common mistake students would think nuclear energy is renewable because it's advanced technology, but it's not. A remark here is nuclear energy is non-renewable. In part E1, we begin with a fully charged cell. Its EMF is 6.0 volts. The current is 5.0 ampere. The time it can run will be a quarter of an hour. And after converting into SI unit, it will be 900 seconds. So what is the energy stored in this cell? The energy stored would be the power times the time, IV times time. So is the multiple of everything you see here. It will be 27,000 joules. On the right hand side is trying to charge up the same cell using solar energy. And the intensity coming from the sun is 380 watt per meter square. It is the intensity. Intensity is defined as the power over area. So you have the intensity equals to power over the product of 0.40 meter and 0.15 meter. Then the power you get should be 22.8 watts. And the useful power should be only 18% of it. So it is 4.104 watts. And how long does it take for 0.104 watts to charge up 27,000 joules? Is power equals energy over time. The power is 4.104. Required energy is 27,000. So the time 6,600 seconds. Part 2 is a very common BS question. Why is some investigation important? Why should we cooperate in certain investigation? And here, let's refer to part 1. Firstly, the existing efficiency of solar panel is low. Also, solar energy is renewable. Moreover, solar energy is clean. It does not emit any greenhouse gases. Question 5 is about radiation. Now we have a sample on the table facing towards a GM detector, but between the source and the GM detector, there is a very thin copper foil. How thin is that? Is to be varied. According to the graph here, the thicker the copper foil, it makes the radiation reaching the GM detector be lower because it's being blocked by the copper foil. In part A, outline how the count rate was corrected for the background radiation. It's a very simple calculation. Just subtract the background radiation from each count. In part B, it suggests that there is a very thin copper foil inserted between the source and the detector already, and it makes the count rate be 810. It's roughly here, there, which means its thickness was 0.25 millimeter. The original thickness is 0.25 mm, and it makes the new thickness be 3 times of that, 0.75 millimeter. And what you need to do is to read the graph and locate 0.75 and get its corresponding reading. It should be 380. Next one, part C, we can see that even though you have two different material, there could be a different detection on a GM detector. It could be because of their blocking ability. And it seems like using the same thickness, lead can block more radiation. So the first point is that now lead is clearly a better absorber. The next point is, for those radiation reaching the detector, there must be no alpha particle. Because alpha particle is very, very weakly penetrating. It cannot pass through a single sheet of paper, not to mention now you have 3.5 millimeter thickness, copper and lead. The last point is that for those reaching the detector, probably there are beta and gamma. Because beta and gamma, they are partly being blocked by copper and lead, but not fully. It still depends on their thickness. Even though there is an absorber of copper and lead, but they are very thin, so beta and gamma may pass through. In part D, we have a decay equation to fill in. It starts from 13755 cesium, going into barrier, and it's shown that the nucleon number is unchanged, so you don't need any numbers to balance the nucleon number, but you need a negative one here to balance the atomic number, and this is a beta decay. For all beta decay, don't forget there is a anti-neutrino. Here in part 6, we have a new experiment. It is a mass spring oscillation experiment, and it went 2 times. The first time you have a 1 kg mass and the first spring with a spring constant K1 oscillates up and down, and then the second one with a heavier mass and another spring with another spring constant K2. And these two oscillations, they are both recorded by the motion sensor, and a graph of speed time graph is displayed over here. Then the part A is about the frequency of these two oscillations. And they share the same frequency as you can see on the diagram. And frequency is 1 over time period. The time period here is 0.8 seconds. So they share the same frequency of 1.25 Hertz. Part 2, we're going to get the ratio of the spring constants. Let's begin with the formula sheet's equation. Time period equals to 2 pi square root m over k. And according to the graph, we can see that they share the same t, which means we can deduce now m over k is equal to a constant. In other words, m and k, they are directly proportional. So k1 over k2 is equal to m1 over m2, and m1 over m2 is going as the question suggests, 1 to 4. In part 3, we are trying to determine the amplitude of the oscillation for test 1, only for test 1. Amplitude, which means the maximum displacement it can get. And don't attempt to read the graph and give the answer directly, because the graph is giving you a speed time graph, not a displacement time graph. What you get on the graph over here, it is actually the maximum speed, not the maximum displacement you can get. But still, it's very useful. Let's put it here. The maximum speed is equal to 4.8 meters per second. How do we use this information? Let's take a look at our formula sheet. Speed is going as this equation. And of course, it could be the other equation as well. Which one should we take over here? Because of the graph provided is in the shape of cosine graph, so we abandon the second one. We take the first one. For maximum speed is happening when time equals to 0, so we have maximum speed equals to 2 pi over t, then maximum displacement and cosine omega times 0. Cosine 0 is essentially 1, maximum speed is 4.8, so by substituting all the number you can get from the question, and boom, that's the answer. Not that challenging. The answer to this one is 0.61. Next one in part 4, now you are going to use your pencil to draw a graph of the potential energy against time. Let's take a look at the given diagram. The object is moving in a loop like here. It started from maximum speed, which means it started from the equilibrium. It may be going down, up, and then down. This is one loop. Let's label these loops as position A, B, C, D, and E. Therefore, on the line number 2, it should be A, B, C, D, and E, respectively. At position A, the spring is neither compressed nor stretched. So at position A, there is a maximum speed but 0 potential energy. At the end, at position E, it is completely identical to A. It will be moving very fast, but it is neither compressed nor stretched. It has no potential energy. How about position C? A, C, E, they're essentially the same points, so they have the same kinetic energy and same potential energy. It's still being 0. You have position A, C, E, like this. How about position B and D? At position B, it is greatly stretched, so there are lots of potential energy stored. At position D, it's greatly compressed, and that is lots of potential energy as well. And potential energy is not going to be negative, it has to be positive. So no matter is it position B or position D, they are both carrying the maximum potential energy, which is 44. And it is happening at time equals to 0.2 and 0.6. So you have two crosses over here for B and 0.6 therefore here. D. Lastly, you join this line using a very smooth curve like this one. And this is the final result of the potential energy against time graph. In part B, we are going to study how does the motion sensor complete the detection of the speed of the plate. It's done by sending a wave, a sound wave going up. And the sound wave is carrying a frequency of 35 kHz. And the sound wave is traveling at a speed of 340 meters per second. Lastly, it's going to hit the plate, but the plate is moving as well, and therefore it will give a Doppler effect and causing a frequency change. To achieve the maximum frequency change, of course the plate must be moving at the maximum speed as well. What is the maximum speed of the plate in test number 2? Is over here, 9.4 meters per second. So now the plate is moving at 9.4 meters per second, and we shall label this value as U subscript O, because it is the speed of observer. And the plate would receive the wave at a frequency of f prime. It is an unknown to be calculated. But this is not the end of the story, because the wave will reflect from the metal plate going down, with once again the speed of 340 meters per second, and the plate now is traveling as a source. Its speed is 9.4 meters per second. Then the wave will reach the detector, which is the motion sensor itself. Then it will receive as a frequency double prime, being the unknown. And take a look at your formula sheets. The equations are going in these formats. Alright, it's time to substitute all the numbers that you know. F prime is unknown, F is 35 kHz, speed of wave is 340, speed of source is 9.4, and then 340 again. So you will get 35.97 kHz. And having this number for the second part, you will have the very final answer. Lastly, to get the maximum change in velocity, we get a simple subtraction, f double prime minus the original frequency, which is 36.99 minus 35. It gives you 2 kHz. For question 7a, you're going to give the definition of electric potential at a point, and it is a very common definition required in past paper as well. And it goes like this. It is the work done per unit charge in bringing a small positive test charge from infinity to the point in an electric field. Make sure you give your answer always in this long phrase, a small positive test charge, and also it is work done per unit charge. And it's always in these wordings, which means once you have memorized these short sentences, you can get 2 marks for free, with no doubt. And in part B, things are getting more complicated. It's better to make a drawing. It begins with a spherical object, and this spherical object was positively charged, and then at its surface, the potential is 53.9 kilovolts, and it is at radius from the center of the object. Another point, which is a further distance. Now it is 2.8 meters from the center of the sphere. So this distance is 2.8 meters, and the potential over here is 7.71 kilovolts. What do we do with these two pair of numbers? We take a look at the equation of electric potential. According to the formula sheet, it goes like this one. And then for the same spherical object, the K and the Q, they're both constant, which makes V times R equals to K times Q, and which is a constant. Then you can put them together for situation 1 and situation 2, like this one. Substituting the numbers into your equation, which makes it radius times 53.9 equals to 2.8 times 7.71. The radius of the spherical object is 0.40 meter. In part C, we are going to study the interaction between the big spherical object and a tiny positively charged object which was very, very far away. Now, on the right-hand side, we have a small q denoting the small object. And this small object is moving towards the center of the metal sphere, which means it's heading to the left towards the center over here. And as it gets closer, it will be here. And it's still moving to the left-hand side. And what is the direction of this motion when you compare to the equipotential line, equipotential surface? An equipotential surface should be surrounding the center of your object, which means this green dotted line and the motion of the small positively charged object, they are perpendicular. And that's the short answer over here, perpendicular. In part C2, it's a very simple calculation. Just get the kinetic energy of the object at that point. But make sure you are going to give your answer in an appropriate significant figure. Once again, it is shown that are bound, and your target is one significant figure, which means your answer should round to 2 sig figs or more. Don't give your answer simply 0.7 millijoules. However, in the questions, the numbers are not always given in SI units. Let's take a look at the mass of the object. It's 0.14 gram, and let's turn it into kilogram. Then it will be 0.14 times 10 to the power of -3 kg. And that's what we need in the calculation. Kinetic energy is half mv squared, half times its mass, and then times the speed, which is 3.1 squared. And the number is 6.727 times 10 to the power of -4. And after rounding, it will be 6.7 times 10 to the power of -4, and which is 0.67 millijoules, which is close to the target. Finally, we have part C3. It is predicting whether the small positively charged objects can reach the surface of the big spherical objects. And let's study before and after reaching the surface. Initially, it was at a certain distance from the center of the spherical object. At that point, the potential is 7.71 kilovolts. Its kinetic energy was the given value, 0.7 millijoules. And because it is positively charged and so as the big spherical object, they are naturally repelling because of the like charge repulsion. In other words, this tiny positive charge object is slowing down as it moves towards the left. And the closer it gets, the stronger the repelling force. Therefore, there could be a chance this tiny positively charged object can never reach the big spherical object's surface. And how do we deduce so? By studying the energy loss as it moves. Because as it is getting closer, it's slowing down, it's losing kinetic energy, and it's also known as there is a work done losing. And the work done, or the energy transfer, is the product of the charge times the change in potential. The work done is the charge of the tiny object, in this case is 2.4 times 10 to the power of -8 coulomb times the change in potential, which is 53.9 kilovolt minus 7.71 times 10 to the power of 3, 1.11 times 10 to the power of negative 3 joules. And this is greater than 0.7 millijoules, which means the tiny positive objects can never reach the surface. If the question command term is determine something, which means your answer must show a comparison, greater than a value, smaller than a value, something like this. Therefore, here is essential. Don't simply leave your answer as 1.11 millijoules. You must give a comparison. That's how you gain full mark. In part A1, we are going to give the magnitude of rate of change of flux. What is rate of change of flux? It is delta flux linkage over delta T. And it is, in your formula sheet, EMF. But we have two EMF over here, one of which is positive 3, the other one is negative 5. And which one should we pick? We pick the negative 5 one, which means the answer over here should be negative 5 millivolts. But we need to give a magnitude only, which means we give the absolute value of it. So the answer is positive 5 millivolts. That's the final answer. In part A2, we are going to convert volts into fundamental SI units. What are fundamental SI units? They are the following 6 units. Meter for length, Kelvin for temperature, kilogram for mass, ampere for current, mole for number of quantity mole, second for time. So we are going to express volt from these 6 units. And let's begin with the equation. Volt is defined as the work done per unit charge, and work done is measured in joules, charge is measured in coulomb. They are neither fundamental SI units, so we need further substitution. Force times displacement, current times time. Similarly, mass times acceleration times displacement over current times time. Now we are ready, because the unit on the right hand side, they are all fundamental SI, which is kilogram, meter per second square, meter, ampere, and second. And simplifying these, it will give you kilogram, meter square, ampere -1, and second -3. In part B1, we're going to give an explanation of why the graph becomes negative in the end. Before we get to the answer, let's take a look on the left-hand side comparing the diagram and the graph. The bar magnet was falling down in the yellow section, and then it will be in the midpoint of the coil. After that, it will be leaving the coil in the red section. And it is corresponding to the graph of, firstly, it gives a positive induced EMF, and when the magnet is right inside the center of the coil, it will be the green part. Lastly, the magnet is leaving the coil, it will be the red section. So our focus is comparing the yellow and the red. Why one of them is positive, the other one is negative. And the comparison is, let's begin with Lenz's law. Lenz's law suggests that the induced EMF would be going in the direction trying to oppose the change which causing it. And then in the yellow section, the magnet is falling down, which means in the yellow section, the induced magnetic pole will be north at the top. Just like here, when the magnet is falling down, the north pole is approaching to the coil, and therefore the coil will induce a northward at the top, trying to repel it. And similarly, when you get to the red section, it will be having a south pole leaving the coil, and therefore we should induce a north pole below the coil, try to attract the leaving magnets. And that's why the yellow and the red loop, they gives you opposite induced EMF direction. The answer goes in this way. Firstly, we define the Lenz's law in a sentence, and then we suggest that the EMF is induced when there is a relative motion between the magnet and the coil. The yellow part, which means the approaching magnet, description is going over here. And then the red section, which means the leaving magnet, its description is going over here. Lastly, the green one, which is happening at the midpoint, is the last part over here. Now in part 2, you're going to give an explanation of why the area under the graph on the positive side and on the negative side, they should give you the same magnitude of area. Which means why the red area and the yellow area, they are in the same size and it's always the same size. No matter is it a big coil, small coil, no matter is it a fast moving magnet or slowly moving magnet, it's always the same size. And the reason goes with the following equations. The first equation at the top, it is the equation you can find in your formula sheets. And what do these imply? The first equation suggests that the EMF is the negative gradient of the magnetic flux linkage against time graph. But it's not what we are looking at. We are studying the second equation, the rearranged equation. It suggests that the negative area under the magnetic flux linkage against time graph is actually the change in magnetic flux linkage. For instance, when the magnet was approaching, it brought 200 Weber towards the system. But when it leaves, the 200 Weber will be leaving with the bar magnet as well. So whatever area on the positive side, whatever area in the negative side it is. Therefore, the final answer is the total area of the graph is representing the total change in flux linkage in the coil. And the change in flux linkage will be the same for going in and going out. Lastly, part C, please give a prediction of what are the changes to the graph when the magnet was dropped from a lower height above the coil. If it was dropped from a lower height, then it would take a longer time in order to complete this change because the magnet is moving slowly now. On the provided graph, the induced EMF finished over here. Now we are going to prolong this one to a later point, for instance, somewhere here. And all the induced EMF will be weaker than the old one because of Faraday's law. Things are getting less rapid, so the induced EMF will be weaker. This could be a fair guess of dropping the magnet at a lower point. You can see that it's reaching a weaker maximum EMF, no matter is it on the positive side or on the negative sides. They are both getting weaker. But the area in the graph should stay the same, which means they are still equal to each other and they're still equal to the old one. Firstly, it's about the time. Because of the magnet is moving slowly, the time will be longer than the old one. And the peak will be weaker as a result of the Faraday's law. And lastly, it's the area under the graph. It should be the same as the old one because the change in magnetic flux linkage is still the same magnitude. In question 9, we have a beam of electron and each of the electron carries an energy of 440 mega electron volts. These electrons, they are heading towards oxygen nuclei. And after passing through the oxygen nuclei, it will start to scatter, creating a scattering angle theta over here. And what properties is demonstrated by the electrons? There are wave properties demonstrated by electron because such scattering is also known as diffraction. And then next question is a show that question. Note that, show that, and about 1 sig fig, which means your answer should be 2 sig fig or more. For now, there's nothing related to the graph yet. You are just converting 440 MeV into joules. To do so, we should solve each multiplier one by one. Firstly, mega, which is 10 to the power of 6, and then elementary charge, which is 1.60 times 10 to the power of negative 19, and putting everything into your calculator, so the answer is 7.0 times 10 to the power of negative 11 joules. In part 3, we are going to study the de Broglie wavelength of the electron and the relationship to the diameter of the oxygen nucleus. Oxygen nucleus diameter is going to be roughly 4 femtometer, which is capital D. De Broglie wavelength is lambda. And how are they related? They are related in this equation in topic 12. Firstly, we should get the de Broglie wavelength using the provided equation hc over E. And after merging these two equations, you can get the diameter easily. Let's begin with the de Broglie wavelength, which is Planck constant, and then the speed of light in vacuum. Lastly, the energy we have previously. The de Broglie wavelength is 2.8 times 10 to the power of negative 15. Next, we take this wavelength into the equation on the left. Angle theta here is the angle to the first minimum according to the graph. So it's roughly here, and it is 46 degrees. So we have 46 degrees over here. The wavelength is 2.8 times 10 to the power of negative 15. The unknown diameter D should be 3.9 times 10 to the power of negative 15 meter, which is 2 sig fig. In part B, we are going to calculate the volume of another nucleus, tin 118. And let's begin with the known information. Oxygen 16. Its diameter is 4 femtometer. And then, based on this information, we are going to study the larger nucleus, tin 118, which is another larger diameter. This diameter, even though it's not provided, but we can calculate. And also, how do we study their volume? Their volume is a spherical volume, so we should prepare for this equation, 4/3 pi r cubed. Over here, it suggests that volume is proportional to the radius cubed. Next, we have the nuclear radius going as r equals to r0 a to the power of 1/3. This equation is provided in topic 12. And it suggests that nuclear radius is proportional to the mass number to the power of 1/3. And also we can rearrange it to make it nuclear radius cubed is proportional to the mass number. So after merging these two informations together, you have volume of a nucleus actually is proportional to its mass number. So let's begin over here. Volume of tin over volume of oxygen is the mass number of tin over the mass number of oxygen, which is 118 over 16. So the volume of tin nucleus is 118 over 16 times the volume of oxygen. And the volume of oxygen is 4/3 pi r cubed, where the radius is half of the diameter. And you can put everything into calculator, then you will get 2.47 times 10 to the power of negative 43 meter cubed. But because of the rounding, we have used 4 femtometer, so we should round our answer as 1 sig fig only. 2 times 10 to the power of negative 43 meter cubed. That's the end of the exam paper. Feel free to leave any comments below and ask any questions if you have. And I will see you in the next exam paper.